Hello, this is lecture 5 on rheometry based on the book of Nonlinear Polymer Rheology published by Wiley.
All right. I want to get over this so that we can move on regarding this arbitrary problem that I sort of indicated to you. So let me give you the summary of what this part is less organized because I just call this as introduction. But these are the topics we went through. Remember, well, I should read. This dynamic oscillatory shear was discussed somewhere here only after I realized I should tell you something about it because many of you did not have my polymer physics class. But logically, it really should be discussed in the beginning. So I'm not going to rearrange the slides because the recording is according to the old slides ordering. So, but basically you have this, after all this repetition was done, I start to realize that I should speak a little bit about oscillatory shear in terms of G prime, G double prime. I think with this makeup, of course, everything we cover should be complete with regard to what is rheology. Please let me know if you find this was too condensed because we're just introducing some definitions here. Let me know if in fact, especially let me know when we move along. If you find something unfamiliar to you, you should raise your hand right away so we can go back and find out what part we forgot. To answer the question about the homework, remember I had a little feeling at the end of last lecture when we say, oh, maybe we have a solution during the semester. And I took an attitude that there should be a way to solve it. And the way I wrote that homework for you with the first line as the question, the several lines below that, I know one of you asked me, was actually giving you a conceptual guide about how to really answer that question, which I previously did not have an answer, partially because of the perspective I took was not quite correct. I will come to that soon, okay? About this, about why viscoelastic material all respond. I know Alex see it as natural, all respond elastically first. To me, I told you that was a mystery for me. We'll get to that, and it's pretty important, I still think. In order to do that, however, I realized that I should also speak a little bit about stress relaxation. Because much of the nonlinear problem, the fascinating nonlinear problem, turns out a great deal to do with stress relaxation protocol. We talked about, where do I see it? I probably should even add it. We talked about startup shear. Yeah? We talked about startup shear. We talked about, I even opened that PPT showing startup shear, if you recall. But we didn't really say much about stress relaxation, which may I add that before we proceed further with this capillary story. So let me just add it to that discussion. Again, this is my fault. I just sort of have the natural impression that we all went through that. Because supposedly this should have a little bit of a prerequisite stress relaxation. I know typing is just as good as writing it. And I can see the writing part. Where's the writing? Here comes back. How do I know this? Okay, here comes the pen comes back. All right. This is a very important mode. Remember we talked about oscillatory shear. We sometimes just call it south. It basically oscillates back and forth. That's a very important mode because the stress is also, you use a small strand, so the stress is also oscillatory. We went through that. And another important mode to investigate rheology or mechanical behavior of your material is stress relaxation. Of course, this just means something fairly straightforward. If you have a strand, let's just take a case of shear. This strand, of course, is nothing but x divided by h, right? So typically, what you do is you all of a sudden move the upper plate a little bit over h, so you achieved a little bit of strand. And that strand, let's say, is on the order of gamma 0. Then your gamma basically behaves this way. It achieves gamma 0 over a time rather small, and you build that stress. You build that deformation to there, and you hold it. Okay, that's what you do. This time it takes for you to build it might be quite small, delta t. And I hate to say that typically when we discuss this as a so-called step strand, people in textbook, some text, would just say it occurs instantly. Of course, in reality, nothing is instant, meaning the delta t is finite. It's never 0. It takes time. The machine takes time to achieve it. Well, you quickly start to recall what we have known so far. The essence of viscoelasticity is internal time scale, tau. So, and of course, I didn't bother to tell you, we only introduced one relaxation time through the Maxwell model. There's a dominant relaxation time. We talk about repetition, where again, there was a dominant relaxation time that we only spoke about. Okay, so we talked about a dominant relaxation time here. What did we have? Here, tau. But it turns out our polymer, of course, is a coil like this. It has a dominant relaxation times. On smaller scale, they are also relaxing. So there is actually a whole spectrum of relaxation times. Wide range, many, many decades. Some are very fast because the segments are very fast, but the overall chain may be much slower. So there are many time scales involved. We're just talking about a dominant one. And that's useful enough for now, because we have so far talked about dominant one. Remember, we talked about of this chain move from there to there. That's obviously the dominant time scale, not the little wiggle, little motions on small scales. So in that sense, this step strand will tend to be valid theoretically as long as it's much shorter. As long as it's much shorter than the dominant relaxation time, right? So as long as that's the case, you have achieved a very sound imposition of the strand. So this is the condition, really. And what do? You watch over that time scale, that little delta t, you watch some stress that you created, watch how it decays. That's called stress relaxation. And if it's a solid, it will not decay to 0. If it's a liquid, it will eventually go to 0. Right? That's the basic story. So if it's a solid, eventually it will just level off. And the reason I said this was necessary was to tell you that you can define, oh, there are two things already here, right? I keep talking about linear response, or at least I started to talk about linear response. It really meant to say that the strand you use is small enough so that the elastic structure is left intact during the step strand. That's linear response. Of course, you have all the liberty to do much more, going to nonlinear response by having a gamma 0 larger. So how large? Large enough to destroy the elastic structure. And we'll speak a great deal about it in the future. For polymers, especially the several 100 billion pounds of polymers we deal with in processing, they are usually untangled polymers, the ones that we are interested in. It turns out that kind of polymer melt, this strand does not need to be that small. It does not need to be much smaller than 1. In fact, it needs to be only smaller than, let's say, 50% deformation, which means half h to the right. Is small enough to leave the untangled polymer intact. So in general, you can see by definition, even if you walk out of a cave, meaning that you know nothing, except the definition of a strand, which is the idea that we're changing the shape of your polymer, and the material resisting the shape change, which means you sense certain resisting force or stress. So it's natural for you to think that the stress that's dropping after this point, or the stress you build, in fact, will be, let's say, proportional to gamma 0, and that is true if you have a linear response. Otherwise, if you have nonlinear response, this could become, in that case, a function of gamma 0. When it's a linear response, they are linearly related, and the coefficient in front of that linearity, by definition, is a stress, GT, and we call it relaxation modulus. In the linear response limit, it is a material function. That's all. That's all you need to know about stress relaxation. And the rest is something that I should at least begin to intrigue you, because as I teach you, this is the part I always love about teaching, right? It calls you to even expose questions that you have not spent enough time dealing with and sorted through. And you just want to use the opportunity of the teaching to sort it out. And a confident professor is one who's never afraid to say, oh, this is something I don't know. Okay, so the next part is quite dramatic, the question I raised. So let me see, I just tried to see where I have properly done this in the book. Nothing better than what I did. so far I think the book has, I see some part that are not as I was, for example, I was starting to try to introduce this GT without discussing stress relaxation. And that's awkward, so for that part, follow me, my lecture here is much better. But generally, subsequently, I did start to reintroduce GT as the discussion of stress relaxation around equation 14, which has this equation, this expression. Okay, now let me come back to a couple of things. That's all in the book. So since it's in the book, it's all easier to deal with because they are already printed. They're very neat forms. I don't have to handwrite them. Now, if you recall, I don't know if I even refined, I don't even know if I refined that question in your homework. But my question was, at least in the case of melts, no solvent, okay, without solvent. Because it turns out that there are cases that a startup deformation will give you a finite stress. I try not to confuse you. If you start with a solution where the solvent is very, very viscous, such that the solvent will just instantly contribute a viscous stress for you. And beyond that, there's the polymer additional contribution. In that case, stress will not start from zero. Okay? I realize sometimes overgeneralizing has the danger of being misleading and incorrect. I'm only talking about non-solvent melt. Magically, it always starts from zero. And for me, that was a mystery. Okay? And today I'm going to change that attitude a little bit. In fact, it's in your homework description how I changed that attitude a little bit. But I did throw this mystery to my good friend, a wonderful polymer scientist, very deeply knowledgeable in the field, my buddy. I asked him the same question. Gee, do you know why the force stress starts from zero? Yes. I think I need to put this. Now, is it better now? Yeah, I think we need to get. This does have a little buffer effect. Oh, I was just saying that I did consult one of the great polymer scientists about the same question, the puzzle. Hey, can you help solving for me? By that time, I already have the homework made. I already know my answer to the question. Okay? But here's his answer. He said, this is all trivial. Okay? And it's okay. And I was, let me tell you why he said it was trivial. It turns out, whatever he said was in my book. So it turns out, he says, oh, I can immediately answer this question because there's such a thing called Boltzmann superposition principle. Well, it's on page 7 in my book. Particularly, it is equation 1.10a. It says stress. By the way, this principle only works for linear response, meaning the strain and stress are linearly related. It's the simplest part of the world. Linear response, linearly. Input, output are linearly proportional. is the simplest part of the world. And if the world is that simple, we can all go home, pack up and go home. And the beauty of the world that we're living in is the high nonlinearity that have fascinated us for a long time. But this question I posed, the homework I posed, survives as a linear response question. Linear response, just as I try to, it all depends on how quick you pick up what I say. Linear response, I already told you generally what it means. You are examining your system by shape change, of course, deformation, without destroying the elastic structure that's in there. That's linear response. So anytime you think linear response, that's the physics. That's the conceptual content there. Okay? So this is, of course, a linear response problem, too. And therefore, that equation says it's that. This is called Boltzmann superposition principle. Okay, so since it's completely trivial, so we are doing a startup shear. So your shear rate, so your strand is increasing because of the startup. So the shear rate is constant. It's just that slope. Therefore, this shear rate is time independent. It drops out, and the shear rate is only applied after t equals 0. So everything drops out. What you have is this. And gamma out comes out. And furthermore, you can just reduce that to saying that is g near t equals 0 because remember, we're considering the first point, right? When t is very small. Okay? So when t is very small, this whole thing is just this integration. I mean, if I teach you this part of integration first time, remember it. This is how beautiful the integration can be done. Remember, integration is nothing but have a curve dividing into many small parts, and each of the part, each of the part is the conceptualization of calculus. Now it's already the first one, so you just take it out. It's still very near 0, and what's left is nothing but the time you have, because the time is very short, and time is gamma dot. Oh, geez, sorry. Why? I know what happens. It's the full screen. And what is that? In any case, this is. See, I'm messing up. My pen is now. See, my pen, I'm pointing here. Is writing there. Let's close it and then reopen it. So I have no way of understanding why this is happening. Okay. Okay. So in any case, this is nothing but G gamma. So this is nothing but the elastic response. When gamma is 0, of course, your stress is 0. So that's why he says, oh, this just comes out of Boltzmann superposition principle. Okay. And remember last time, if I said it or if I not, I say it again. I also say miraculously and strangely, the Maxwell model also captured this response very nicely. I, in fact, spent some space talking about it in figure 1.4. Well, it turns out the Maxwell model has the same structure as this Boltzmann linear Boltzmann superposition principle. In fact, the Maxwell solution for the problem is exactly the same as the Boltzmann expression, except your G, according to Maxwell, is of this form. So you end up having the same result. So if you trace back to, then you ask, gee, how do I know Maxwell model? How do I know the Boltzmann superposition, where this comes from? Well, if you go back to my book, it basically says it comes from assuming that the stress will be elastic-like. And it turns out, there's a discussion on page 7. I'm not going into it at all. But basically, it adds up as you have more and more. So eventually, you get an integration of it. So that is very unsatisfying. In other words, I further pose the question, how on earth Boltzmann knows this is how material respond? I mean, it goes back to Alex's question. Alex basically says, gee, you just should do it. You just should do it. It should be just elastic initially. And my friend was brushing me away, saying this is trivial. So let me take a different attitude to this. Of course, I wanted to know the answer before I consulted my friend, my colleague, and that's what happened. So it turns out this is the way I typically do my science. It turns out the story is quite remarkable, in fact. So let's be patient. So we talked about last time, we have a clue. Somehow, at the beginning, when I first just deform it, my material, as if, let's not speak about it, just let's calculate, as if it has some viscosity. Well, it should have some viscosity, sure. Let's just calculate. It has a viscosity. Let's call that viscosity eta 1, just for the sake of argument. Okay? And then you have a shear rate that you already applied, that's gamma dot. So necessarily, you are generating this much stress from the first moment. Yeah? Fine. And now let's figure out, well, you can do a few things, but let me do the other part. Let's figure out what happened to the elastic part of my material. Well, we know that elastic thing has a stress of G. And let's say we're just examining, just like we did, we're just examining the first bit, the little delta t. Yeah? As your instrument can resolve, very small delta t, right? So of course, then, because it's Hawking's law, so the strain that occurs is of course delta t gamma dot, right? So let me write it down. So it's this, and it's gamma dot delta t. And then I can even do a little bit more to proceed. I can even start to reduce things a little bit. I can even still introduce a Weissenberg number. So I can multiply a tau and divide a tau. And then this part, of course, is Weissenberg number. Okay, so I can rewrite this as G Weissenberg number delta t over tau. Weissenberg number can be anything, can be 1, can be 10. We don't specify it here. But of course, this thing will be much smaller than GWI because delta t is chosen to be much, much smaller than 1. It's much smaller than tau. So let me redo this part. I can also add a tau and divide a tau. And I'm going to realize that this is my Weismer number again. And furthermore, we're going to use Maxwell-like relationship here. So I will rewrite tau as G, and what's left is eta 1 divided by eta. Yeah? I'm not playing magic, right? This is what it is. And yeah, go ahead. Eta is defined just like that. This thing is always something that you can use when you don't have a model. And this comes, of course, from Maxwell model. Yeah. I mean, what I mean is you can flip them around. You can do anything you want. It's the same thing. You get my point? Yeah. Yeah. So, because obviously, in the second equation, G occurs. In the first equation, I'm regenerating everything in terms of G. Okay. This is the artful thing that very trivial to do, but you can see how beautiful it is. Now, the rest, I make the following claim, that as long as this is comparable to this, follow my logic. As long as the viscous stress is comparable to the elastic stress, our puzzle is solved. You get my point? In other words, if the viscous stress is only as large as the elastic stress, then we don't see the viscous stress because viscous stress goes to zero. Do you see my point logic here? This is a very crucial part of the logic, right? As long as it would be, if my initial stress is nearly zero, then twice of nearly zero is still zero. Do you get it? Even if my total stress, you see the whole idea is, even if my total stress is that. Yeah, so, okay? Now, all you need to realize is what this means. It just means eta 1 is comparable to delta T over tau. Yeah? So I can further expand. Because we know, as an experimentalist, I know this is true. Of course. Not of course, because I know my tau, let's say it's 10 seconds. My instrument resolution, let's say, is 10 milliseconds. So I further indicate for you that this now comes to the sort of what I already said in the homework description. And my colleague, I think, didn't really appreciate it as much as I do, because he threw, none of my discussion has anything to do with Boltzmann for superposition principle, okay? Nothing. It turns out the mystery that I have proposed to me and puzzled me for years that I cannot solve is one, what I call, is a feature or it's a phenomenon of first principles. I know you don't hear this word a lot of times. Physicists like to use first principle understanding of it. F equals ma, that's first principles. In other words, what this behavior is telling you is what it is. You cannot go, one day I have to go back to my friend and see if we can derive this for me. But for now, this is first principle. it's always, I teach my students, this is always my habit. If something is not artifact, it's always true. That observation, that experiment is revealing some fundamental truth, whether you understand it or not. So it turns out an amazing part of the puzzle is this. You have a gigantic structure, which is this entanglement. Associated with that structure is a huge relaxation time and a huge viscosity. Okay? But to explore it, to explore that structure and the associated viscosity takes time, which you don't have. So this is the first principle. That this Mother Nature tells us there is the principle that no matter how viscous your material is, the reason you have such a viscous material, or rather, if the only way you can sense that high viscous material is you allow yourself to explore that structure. And this goes a little bit back to what Alex said. If that elastic structure has no chance to rearrange, then there's no dissipation, there's no viscosity. By the way, that language is what also my friend said, but it's not coming out of Boltzmann, per se, in my opinion, at least. So when the time is short, you only have access to a very small viscosity. That's the bottom line. Mystery solved. And perhaps anyone would have just overlooked it. Who cares? I mean, it's always true. The fact that I care is because I told you that there are professors after the end of their career were confused about whether there is flow initially or not. And this has everything to do with understanding whether there is flow or not initially. And my argument was always that there is no flow if your stress is starting from zero. There is no flow initially. Okay? Well, however trivial this issue is, I don't think so. I think like, I certainly had not had enough appreciation that viscosity takes time to exhibit itself. Question? Yeah. Mm. Yes, I mean, I don't mean to use Blackboard. I mean, the best, Alex, you are really saying is you're talking about a dilute solution. Okay? The solvent contribution will be there. Remember, that was the same question. There is no question in a dilute solution. You guys should all know that limit. That there is the solvent viscosity, and solvent viscosity means what? The solvent in this case means what? It has a, let's say, call it tau 1. It is very, very short compared to this chain relaxation time, which we know in dilute solution is so-called Zim relaxation time. So there is no question in my mind, I don't have data with you, that this contribution will show up right away, plus a polymer contribution. There's no without question. I know in a limit, not the dilute limit, but rather concentrated limit, as I said. But this thing is huge. This solvent is huge. In that case, this term does right away pop out compared to the additional contribution from polymers. Yeah. And so it's a matter of comparing. So So even a typical polymer solution, it doesn't show up. Only because the solvent viscosity is simply not high enough. Remember, high or not, it's all discussed here already. High or not, it's all a matter of whether your solvent viscosity is higher or not compared to this viscosity, eta 1, that comes from the polymer part. Since this is gigantic, this can be quite large and still have the problem of being small by definition. See it, right? The definition is here. Remember, to get a reasonable parameter is here. If this thing is a 1,000th, of course, it's 1,000th of this level, then 1,000th of that level is 0, right? We treat them. See, so everything works out that way. Okay. Any question? I don't apologize for spending the time on this because I don't think this is so deeply understood or at least so deeply discussed in the open literature, in any textbook. And certainly I doubt it was discussed in your learning of the polymer rheology. But it's there. And not only it's there, it tells us something quite remarkably. My friend clearly knows that the viscous thing doesn't kick in right away. And he was perhaps just using Boltzmann to say, hey, Boltzmann can also show you it doesn't kick in. So my disappointment is to use Boltzmann superposition principle, but rather just exactly why. I guess that's the question. Can someday have a statistical mechanical theory that describes why viscous term cannot immediately show up due to the large structure of the. But I think I'm conceptually satisfied. I think it seems like I learned a little bit. It seems like something to be viscous is for something to wait for the structure to rearrange, and that big structure to rearrange is giving rise to the big, to the big dissipation, big viscosity. Okay, so with this we can move on. I think everything is mapped here, including this homework. So I put it in there, and we are here, more or less done. So we can just say a little bit about this, and then we can move on to the real content of this course. Most of what I'm going to say is in chapter 3. Chapter 4 and 5 were just a little bit of a diversion from it, which we will cover when the need arises. But let me just give you the rest of the logic of this. Why is it? Jesus. When we are here, I think I again had no plan to describe shear in the more conventional manner. I felt maybe that is not quite appropriate. So let me just go back to this outline and tell you what I could do. So we have this. I it's not my intention to ignore the shear part, the shear rheometry, okay? In fact, much of what will be discussed involves shear rheometry. So let me just, the issue is it's very, I wouldn't call it boring, but it's very, very standard. So I just did not wish to have to go through them. Standard in the sense, not only it was in chapter 3, not only it was described in chapter 3. So let me just use this space, probably enough to give you the completeness of this. This shear rheometry has a lot of challenges, actually. So perhaps it's wrong for me to omit it. But rheometry of shear, the simplest one is what we already did. Parallel plate like this, and you start to move one of the plate to the right. Either some speed or certain magnitude, depending on what you do. And you can see this device, this configuration is not suitable if you want to shear forever, because very quickly the upper plate will be over the lower plate and beyond, right? By definition, if it's just two plates like this. Okay, so if you want to design, you obviously want this L, if this is the height, you want L to be much, much larger than the height in order to be able to achieve quite a bit of shear. But still, it's limited. I mean, this, we can call it aspect ratio. Eventually, it is a matter of engineering. It becomes very severe in terms of how good your alignment is, right? But don't brush it away, this geometry. If you just, as we said, step strand is perfectly fine. For example, you can move, let's say, make a 300%, or I know the way I did it is quite, is not sufficient. So you can, so you have to draw a very thin gap. So you can probably make a, something like 400% deformation, like that, right? It would mean that this is about 4 times of the H. And that's a lot. Turns out 400% deformation for your dear polymer is a lot. So this geometry, at least we can do some step strand, perhaps to 3 or 4 strands. But as you wish to draw, to shear more, this becomes inconvenient, impossible. Therefore, there are no commercial instrument based on this simple geometry. So the next one, of course, is the so-called, so if you call this linear displacement type, the next one is rotational. I said it's in the book, that's why I didn't really wish to even bring it up. Rotational configuration. And there are obviously 2 possible types. One is, there are 2 circular disks. One is rotating relative to the other. So for example, the second one fixed. If you look on top, it's circle. So it's rotating. So it turns out locally that's shear because the velocity is tangential going in a direction perpendicular to the gradient direction. So it is shear. And you can do it continuously forever. The trouble with this is the shear rate is not constant because the shear rate depends on the R. So the shear rate is higher as you go further away from the center, linearly. Remember, when I discuss this, again, I assume shear is homogeneous. Don't get confused about this too. The shear is homogeneous across the gap, but radially, they are not the same shear rate, and it increases as you move away from the center. And the way to overcome that was to use cone plate with an angle, which is usually quite small, not what I draw, usually 5 degrees or less. Same thing with one of the surface rotating. It could be that your lower disk is fixed. It could be the other way around. The cone is fixed, the disk rotating. It doesn't matter. So this all achieve a shear, and this gives you a shear rate, which is proportional to omega is angular velocity. This is all in the book. What I can emphasize for you is how nasty this kind of rotational shear device could be, because it necessarily leaves the sample with a free surface. Necessarily. Remember, one day I said I want to use saliva with my water to demonstrate. It's the same thing. Basically, the surface tension is holding the sample at the meniscus, so-called. And this is a disaster when you shear very strongly. In the nonlinear response, we have hardly talked about yet. When you sheared very fast and sheared a great deal, you meet an enormous problem that nobody on Earth knows how to solve it. In other words, our shear device is far from a perfect apparatus because of the free surface that's inherently there. If you guys have an idea about how to get rid of it, let me know, because we should be able to, you should be able to make, I will instruct you to make a pattern on it and move the science forward. Having said that, this is why, not do that. Having said that, this is why there's chapter 5, which we're going to skip. So chapter 5 talk about the improving, try to overcome that problem, okay? And one way to improve it, well, this is already a cute way to improve it. I'm going to omit it. But there is a second one to improve it, which is this. You are not only interested in prescribing the deformation field, which is linear, if you pray to God that there is no inhomogeneity, but also you want to make a mechanical measurement. If your edge is going unstable, if your edge here is going unstable, it's going to affect your measurement by definition, because over here, some complicated things happen so that you no longer have simple shear. And this is for all, potentially all viscoelastic material. You could, in principle, encounter that problem. So a clever design by someone that goes back to Masner, is one of the person who initially did, was you try to overcome that by protecting your sample or protecting your measurement. And it requires only one type of rheometer, which is from TA, such that you let some nasty things happen, but as long as this nasty things has not propagated to where the red part is, then this part is still nicely undergoing simple shear. And the stress response is collected by this center disk with the ring protecting it, but they are totally decoupled, meaning you're leaving it with a gap. So in that limit, you could overcome the mismeasurement from, you don't overcome what's happening here. That never can be overcome. But at least you could interrogate your material away from where the nasty things occurs and get the right rheological measurement this way. Okay, so this is why in a short while I'm covering chapter 5 was the reason we had chapter 5 dealing with this edge effect. And then chapter 4 is on a technique that in the future we will talk about. So that's the rotational device, the issue of it. Of course, in this linear device, you have the same issue, meaning it's open, meaning all this is all this is a free surface here. And things can happen, bad things can happen. And by the way, this is why the step strand is a way potentially that could minimize this. Because you don't shear like crazy forever. You shear a certain amount and you stop. Okay. Any question? So this is just sort of, all this so far is sort of just some background knowledge, nothing really serious in the sense of requiring a great deal of brain power to be exerted. So if we follow, just because we do a lot of extension, so the only part that we have yet to talk about, we call 2, 3 was shear, I did the way I did, is really say a little bit about extension. Oh gosh. Extensional rheometry. And of course, you can get very fancy about it. For example, if you try to examine, extension means stretching, okay? So, of course, in a if you have a material that can maintain its integrity, I can just draw a block like this, and the next moment you just stretch, it becomes thinner. But if this is a piece of honey, of course you can't do it. It doesn't mean you cannot try to change the shape of a piece of honey in this extensional manner. Then how do we do it? Well, there are ways that we are not going to concentrate on. For example, you can have your honey have 4 cylinders in your honey and have 4 cylinders rotate like this. So the honey will go out like that. Right? By definition. And that causes a stretch in the middle. In fact, the middle is called, just for your language, a stagnation point. So that's just one way. You can even think about a simpler way. Have a wall and shoot your jets on the wall. And the material will just try to stretch away. And you can have 2 opposing jets guided in some way, and then the fluid will just try to move away like that. So there are scenarios that you can think about, but that's not our concentration because The several hundred billions of polymers we process every year is typically done in the melt form, not really water or honey-like. And so, for example, certainly in rubber industry, when we process to make a tire, the issue of extension becomes important. When we blow a film blowing, film molding, there's the issue about extension. So of course, extension is a second component, like shear, a very dominant component that's involved in processing. So we separately discuss it, shear versus extension. So it's only just a matter of language. Just to keep you interested in this topic, I want to indicate how lucky we are in this world. So, and I will later explain why we're so lucky. But in any case, if it's a piece of rubber that you can make a sheet like a sample and you want to examine it, there were previously people trying to grab that piece of sheet with, if I look at the cross, with 4 rows and try to grab it and try to move this sheet away. Get it? A roller that squeeze onto the piece, bottom and top, and try to move it away, circulating this way, and try to bring this material, extend it. That was the old design by Meissner, actually. The one I mentioned about the CPPs, cone plate, partition plate. People have used this, so this is, the gravity is down here. And this is bad, because it sags as a melt, right? You have a sheet, basically you have this sheet, which is not a solid. It's in that liquid state. And you're trying to use 4 rows, try to stretch it, but this thing just will sag. So only some, less than 20 years ago, we have a local guy working in Goodyear on his spare time, invented a very convenient tool to do the extension so that even when you have a rotational rheometer, which means you have a shaft that rotates, he can use that rheometer to perform extension. And the way he does it is he builds 2 cylinders and with a base so that you can rotate one of the cylinder by mounting it to your rheometer, rotational rheometer. And your sample is being mounted on this 2 cylinder. And as this cylinder rotates, your sample that adhered to the cylinder will get stretched. And what it overcomes, however, is instead of sample being like this, the sample now is like this. Okay? The ability to overcome sagging is by how much? Is by the ratio of thickness to the height. Well, our sample typically is not this thin, but if this is this thing, that would be a factor of what, 1,000? Because this paper is what, 50 micron? And this is a huge. So in any case, it's a lovely design for 2 reasons. It overcomes sagging. For you guys do soft materials, this could be a way. It overcomes sagging. And secondly, you can immediately install it on commercial rotational rheometry. So that was a technological advance, very, very, very convenient and useful. So with that, I had said enough to motivate you to think about the language of it. And the language of it, I know I have 5 minutes, probably is enough. The language of it is quite trivial. Of course, it's all described in careful detail. Very trivial, though. Very trivial. But it's described in page, but I will go through it. But if you miss it, it's only, what? Less than a page on page 63 to 64. In less than a page, half a page. It captures everything we need to know and say, which will be enormously important in the subsequent discussion of nonlinear rheology. Okay, so that's why I kind of singled out the capillary, which we will use next time discussing wall slip, and extension, which we will also discuss extensively because of the confusion that is associated with this geometry or this mode of deformation. If I have time, I probably would even mention already about why this mode is so different. Okay? Perhaps we should say that right away, why this mode is fascinatingly different. Okay, let's see it, how it's different. Remember when we had the shear? We use this configuration to conceptualize, to discuss it. If you have cone plate, it's the same discussion. What part I mean? I mean the shear plane has an area that is fixed during shear, right? The sample is always in contact with these two surfaces. The loading surface, the surface where the load occurs, is constant. Yeah? By definition, I mean, I'm just pointing out something completely trivial. But what is not the same is extension. The loading area is this, right? Is this. That area keeps changing. That loading area keeps changing as I draw thinner and thinner. Just something to keep in mind. So all of a sudden you see it's utterly different from shear, and this difference has caused considerable confusion in the field. Confusion that I assume has not been fully resolved by confusion that we have pointed out where the confusion is. That we will talk about much later. So in any case, we have to be able to walk before we run. And of course, we just need to introduce some of the notations. You have a cross-sectional area, you have a length of your sample. Of course, your length in the beginning, we can call it L0. And you may be drawing with certain speed, V. And for convenience, you can just think about one of the surface is kept fixed so that you're just moving the other end. In fact, that's what you do in Ingstrom. A so-called stretcher or Ingstrom tester. But in this geometry, of course, both ends are moving, but it doesn't matter. It's the same thing when we come to think about shape change. When we come to think about if you sit in the middle of your sample, you will always see the two ends moving equally away. Again, in the limit of homogeneous extension. The rest is completely trivial, for example, because you are moving with velocity v, you are increasing the length. per unit time. Okay, and what you can further say is that's just the velocity of moving one end. It does not give you a sense of how fast you are stretching. Because obviously, if my length is twice as long, if I want to compare with a sample that's half of the length, then the one that's twice long should have a velocity twice as large, right? If we want to compare. So in other words, of course, it's this that gives you a sense of how fast you are stretching, by definition. Okay? If my L doubled, my speed also doubled, then I'm comparing apple to apple, then we're talking about applying the same rate. So it is this quantity that captures how fast we are stretching. Just like previously we had for shear that we eventually was able to show, and it's also in the book, in the homogeneous limit, the shear rate is, see, another way to appreciate, the shear rate is constant as soon as you are maintaining a constant speed on the plate, because this gap is constant. So associated with this problem of loading area is changing, which I just remarked for you, for extension. You have to think about whether your stretching rate is changing or not. Your stretching rate is changing or not depending on whether you are keeping your velocity constant or not. Since you are stretching, your length is keep increasing. If you want to keep this constant, then obviously your velocity also need to increase. See the point? So you can discuss in the limit where this is constant. And we have a symbol for it. We call it epsilon dot. And we call this Hanke rate. Hanke is a person, one of the pioneers in the field of examining materials undergoing extension. So if let me finish it. In fact, I know I'm past my time, but oops. So if I give me just 1 second. If I have this V over L, that's dL over dt over L, then it turns out that this is nothing but this, and so you can integrate. And you can start from L to L0. So this is your initial length. This is your final length. And we typically call the shape change the stretching ratio, which is L over L0. this integrated strand, Hanke strand, we call it Hanke strand, is just a definition. And you can see it's related to the stretching ratio in this manner. Moreover, the rest is all simple. You can find, for example, velocity will change exponentially fast. Length will also change exponentially fast in the limit where the stretching is maintaining a constant Hanke rate. Of course, this. Of course, this proves V over V is the same at the beginning. It's the same everywhere. So all this is discussed in chapter, in page 63 to 64. Any questions before? So this finishes the language we have. We have a stretching, we have a stretching ratio, we have a Hanke rate, we have a Hanke strand. And I even told you about how profoundly different. To have a constant shear rate is just moving the plate constantly at a constant speed. Whereas if you want to stretch a piece of material with a constant Hanke rate, you have to stretch it. Basically, if it's Ingstrom, it gradually, slowly, eventually the speed just exponentially grows because your length grows exponentially. This is a typical mode for people to examine polymer melts so that we could have a sense of what is 100% strand. 100% strand, by definition, is going to take a time of 1 over epsilon dot, just by this expression, definition. And epsilon equals 1 is, by definition, 1 log lambda is 1, and that is lambda is about E, which is about 2.7. So we're coming back home talking about what it takes to change the shape of your material by a considerable amount. In shear, we talked about 100% deformation, 1h to the right over the height. Here, we can also at least speak about when I almost tripled my length, 2.7, how long it takes. Well, it tells you exactly how long it takes. It takes the reciprocal of the rate, or if you like better, L over V. Since we're down in the constant Hanke rate limit, that for your convenience, that is also the time you know without even doing experiment, because that's your initial length versus your initial speed. And that analogy, of course, is very strong compared to what you had in shear. So it's knowable for us to ask, it is easy for us to ask the question, how long it has taken us to make a considerable shape change, which is this. And of course, the whole idea is not figuring out T1, but rather figuring out whether, I don't want to write 3 times, whether this is larger or smaller than your dominant relaxation time, right? That's the question, right? Same. And similarly, Hanke rate, Hanke, Weissenberg number for extension is defined in the same way. I always prefer to remind you is the ratio of the time. That's it. We're really done, ready to launch the whole discussion on rheology that will be fresh, perhaps even to Alex and Daria. Okay. Thank you for bearing with me. I know